Hey there, science fans! Today, we're diving into the fascinating world of HPLC, or high-performance liquid chromatography. Don't let the big words scare you, it's simpler than it sounds. Imagine a racetrack for molecules. That's essentially what HPLC is all about. In this race, we're trying to separate different molecules within a mixture. Just like runners have different speeds, molecules interact differently with a special material called the stationary phase inside the HPLC column. The faster molecules shoot ahead, while the slower ones lag behind. This difference in speed allows us to identify and even quantify each molecule, which is super useful in fields like medicine, food analysis, and environmental science. Pretty neat, right? Okay, so we know HPLC separates molecules, but how does it actually work? Let's dive deeper into the fascinating world of high-performance liquid chromatography, or HPLC for short. Let's pop the hood and see what's inside this molecular racetrack. Imagine you're looking under the hood of a high-performance sports car, but instead of pistons and spark plugs, we have some incredible scientific components. First up, we've got the mobile phase, which is a liquid that carries our mixture through the system. This liquid can be water, methanol, acetonitrile, or a mix of these solvents, depending on the nature of the molecules we want to separate. Think of it as the track surface for our molecular runners. The mobile phase is crucial because it interacts with the molecules in our sample, helping to push them through the system. Next, we have the pump, the engine of our system, which pushes the mobile phase through the column at a steady pace. This pump needs to be incredibly precise, maintaining a constant flow rate to ensure accurate separation of molecules. The column. This is where the magic happens. The column is typically made of stainless steel and packed with tiny particles that make up the stationary phase. It's a tube packed with that special stationary phase material. These particles are often made of silica and are coated with various chemical groups to interact with the molecules in different ways. And of course, we need a detector at the end of the race. The detector is like the finish line judge, identifying and quantifying the molecules as they exit the column. It spots the separated molecules as they cross the finish line, telling us what they are and how much of each is present. The detector can be a UV detector, a mass spectrometer, or even a fluorescence detector, depending on the type of analysis we need. Lastly, the whole shebang is controlled by a computer system because even scientists need a little help managing this molecular marathon. The computer system not only controls the pump and detector but also collects and analyzes the data, providing us with detailed chromatograms that show the separated molecules. Before we even start the HPLC process, samples need to be prepared meticulously. This involves dissolving the sample in a suitable solvent and sometimes filtering it to remove any particulates that could clog the column. The sample is then injected into the HPLC system through an injection port. This is a critical step because the amount of sample injected can affect the separation and the accuracy of the results. Calibration is another essential part of the process. Scientists use calibration standards to ensure that the HPLC system is working correctly and that the results are accurate. These standards are known quantities of substances that help in creating a calibration curve. Once the sample has been run through the HPLC system, the resulting chromatogram is analyzed. Each peak on the chromatogram represents a different molecule, and the area under the peak indicates the quantity of that molecule. Scientists often discuss the results with colleagues to interpret the data accurately. This collaborative effort ensures that the findings are reliable and can be used for further research or quality control. All the data and observations are meticulously recorded in lab notebooks. This documentation is crucial for reproducibility and for future reference. After the analysis, the HPLC machine needs to be cleaned and maintained to ensure its longevity and accuracy for future experiments. This involves flushing the system with solvents to remove any residual sample or mobile phase. The columns are also stored properly to maintain their integrity. Proper storage conditions are essential to prevent any degradation of the stationary phase material. In many laboratories, multiple HPLC machines are used simultaneously to handle the workload. Each machine can be set up for different types of analyses, making the lab a bustling hub of scientific activity. The data obtained from HPLC analyses are often presented in meetings and conferences. These presentations help in sharing knowledge and advancements in various fields of research. Finally, the results are compiled into research papers and reports. These documents contribute to the scientific community's understanding of various substances and their behaviors. And there you have it, the insides of an HPLC machine and the meticulous process that goes into separating and analyzing molecules. It's a fascinating blend of engineering and chemistry, all working together to unlock the secrets of the molecular world. Hold on to your lab coats, folks, because HPLC isn't a one-trick pony. High-Performance Liquid Chromatography, or HPLC for short, is a versatile and powerful tool in the world of analytical chemistry. It's like having a Swiss Army knife in your lab, with each blade designed for a specific task. But remember, not all HPLC methods are created equal. Just like there are different types of races, from sprints to marathons, there are different flavors of HPLC, each optimized for specific separation challenges. Whether you're dealing with small organic molecules or large biomolecules, there's an HPLC method tailored just for you. First off, we've got reverse phase HPLC, the most popular kid on the block. This method is widely used because of its versatility and efficiency. It's particularly great for separating nonpolar compounds. Imagine it as an obstacle course for molecules where the stationary phase is nonpolar and the mobile phase is polar. The nonpolar molecules stick to the stationary phase longer, while the polar molecules move faster through the column. This difference in movement allows for effective separation. Then there's normal phase HPLC, the opposite of reverse phase. This method is less common but still very useful, especially for separating polar compounds. Here the stationary phase is polar, and the mobile phase is nonpolar. It's like flipping the script where polar molecules interact more with the stationary phase and nonpolar molecules pass through more quickly. This technique is particularly useful for compounds that are difficult to separate using reverse phase HPLC. It's all about finding the right balance. The choice between reverse phase and normal phase HPLC depends on the nature of the compounds you're working with and the specific separation goals you have in mind. For separating really large molecules like proteins and polymers, Size-Exclusion HPLC is our go-to. This method is also known as gel permeation chromatography. Think of it as a molecular sieve, separating molecules based on their size. Larger molecules pass through the column more quickly because they can't enter the small pores of the stationary phase, while smaller molecules take longer as they navigate through these pores. This technique is invaluable in biochemistry and polymer science. And last but not least, we have ion exchange HPLC, which separates molecules based on their charge. This method is particularly useful for separating ions and polar molecules. With so many options, there's an HPLC technique for almost every separation need. Whether you're working in pharmaceuticals, environmental science, or food chemistry, HPLC offers a tailored solution to your analytical challenges. So, next time you're in the lab, remember that HPLC is not a one-size-fits-all tool. It's a customizable, adaptable, and incredibly powerful technique that can be fine-tuned to meet your specific needs. Happy experimenting! Alright, science enthusiasts, we've got our HPLC system all set up. Now let's talk about the control panel, those operating conditions that fine-tune our molecular race. First up, we've got flow rate, which controls how fast the mobile phase zips through the column. Think of it as adjusting the wind speed on our racetrack. Then there's mobile phase composition, which is like choosing the type of track surface. We can use different solvents in different ratios to optimize the separation. Temperature is another crucial factor. Just like athletes perform differently in different temperatures, molecules can be affected by heat too. And last but not least, we have injection volume, which is like deciding how many runners to send out on the track. Getting these conditions just right is crucial for a successful HPLC experiment. We've separated our molecules, but how do we actually see them? This is where the magic of HPLC detectors comes into play. These detectors are the eyes of the HPLC system, allowing us to visualize and analyze the separated components of our sample. Without them, our separated molecules would remain invisible, and all our hard work would be for nothing. That's where our trusty detectives, the HPLC detectors, come in. These devices are designed to detect and measure the presence of different molecules as they elute from the HPLC column. Each type of detector has its own unique way of identifying and quantifying the molecules, providing us with valuable information about our sample. One of the most common detectors is the UV-Vis detector. This versatile detector is widely used in many laboratories due to its simplicity and effectiveness. It operates by shining ultraviolet or visible light through the sample as it exits the HPLC column. It shines UV light on the separated molecules and, as the light passes through the sample, some of it is absorbed by the molecules. The amount of light absorbed is directly related to the concentration of the molecules in the sample. By measuring how much light is absorbed, we can identify and quantify them. The resulting data is displayed as a graph, with peaks corresponding to different molecules. This allows scientists to determine the concentration and identity of each component in the sample. For light-sensitive molecules, we have the fluorescence detector. This detector is particularly useful for detecting molecules that emit light when excited by a specific wavelength. It's like a blacklight for molecules, making them glow so we can detect them. When the molecules are exposed to the excitation light, they emit light at a different wavelength, which is then measured by the detector. This glowing effect allows us to detect even very small amounts of light-sensitive molecules, making the fluorescence detector highly sensitive and ideal for certain applications. Then there's the refractive index detector, which measures how much light bends when passing through the sample. This detector is based on the principle that different substances bend light to different extents. It measures how much light bends when passing through the sample. When the sample exits the HPLC column, it passes through a flow cell where the refractive index is measured. The change in the refractive index is proportional to the concentration of the molecules in the sample. It's like looking for distortions in a funhouse mirror. The refractive index detector is particularly useful for detecting molecules that do not absorb UV light, providing an alternative method for analysis. And for identifying unknown molecules, we have the mass spectrometer. This powerful detector provides detailed information about the molecular weight and structure of the molecules in the sample. It measures the mass-to-charge ratio of ions. The sample is ionized and the resulting ions are separated based on their mass-to-charge ratio. This data is then used to identify the molecules and determine their structure. Each detector has its strengths and weaknesses, and choosing the right one is crucial for accurate and reliable HPLC analysis. The choice of detector depends on the specific requirements of the analysis, such as the type of molecules being analyzed and the sensitivity needed. By understanding the capabilities and limitations of each detector, scientists can select the most appropriate one for their needs, ensuring that they obtain the most accurate and reliable results possible. The right detector can make all the difference in the success of an HPLC analysis, providing valuable insights into the composition and properties of the sample.